All right, welcome to today's class in Mathematics 2. Let's get started. One last reminder, no new topics next week. Instead, we'll talk about whatever you wish to discuss. There's a tweet bag for collecting any questions, any remarks, anything you would like to discuss. Please just leave a comment on that tweet bag. You can access that here. There's a link for week number 14, which is also on the Moodle page. All right, so for today, we'll discuss the last topic that will be relevant for the exam, which is Green's theorem. Just as a quick reminder of what we discussed on Monday, you remember we talked about a specific type of vector fields, which is called gradient fields. A gradient field basically is one that has a potential, so that means you have a function, usually called capital F, from Rn to R, such that the gradient of that function is our vector field. And the vector field that have a potential like those are called gradient fields or conservative fields. And then that function F is usually referred to as the potential or the antiderivative. We've seen a couple of examples of that. We've also discussed the question of when such a field exists. So if you have a vector field and you want to see if it has a potential, then one thing you can do is you can try and compute a potential, of course. If you're successful, you have proven that it has a potential, so the field is conservative. Or you'll find along the way that there is no possibility of computing that. There may be some other possibility, which is looking at these so-called integrability conditions. Any vector field that has a potential needs to fulfill those integrability conditions for all ij's. So basically, you look at all the components of a field and all the partial derivatives of those components, and the index of component and of partial derivative, those should be interchangeable. Right? So whether you look at vi and differentiate that with respect to some xj, or you look at vj and differentiate that with respect to some xi, that shouldn't make a difference. Any conservative vector field will fulfill those conditions. So if they're not satisfied, you know that there can't be a potential for that field. It's not a gradient field then. If they're satisfied, in general, you still don't know whether that field is conservative. But there is a condition that you can add to that, and that is being the domain being simply connected. If that is the case, then these integrability conditions will be sufficient to know that your vector field is conservative. So you have a potential, even though you might not know what the potential is. Hi.
Sorry for interrupting. I have a cocktail booth and I thought maybe you can use some orange juice with cranberry.
That's very nice. Thanks.
Have a nice day.
Yeah, same to you. All right, where was I? Gradient fields, right. So that much we discussed on Monday. We also had a look at some examples. And for today, we'll be concerned with Green's theorem. Basically, we've seen two different notions of integration by now. We've seen volume integrals and we've seen line integrals, which are pretty different things. And the natural question to ask, of course, is there a connection between those two? And the answer is, in many cases, there is a connection, but it is pretty specific. And Green's theorem is one example for such a connection. There are other theorems of more or less the same or similar types, but this is the one that we'll discuss. What that theorem says is basically if you have a domain in R2, so Green's is only applicable in R2, not in other dimensions, and you have a vector field defined on that domain which is continuously differentiable, and then a compact set, I'll call that B here, a compact set that lies in that domain. Remember, compact means closed and bounded. And it should have some interior, so it's not a completely trivial set, not just a single point or something like that. Then you can look at the boundary of that set. And basically, if that boundary has a certain structure, then there is a connection between the integral of the vector field along the boundary and the integral over B itself, right, the volume integral, of a function that is connected to the vector field, and it looks like that. Yeah, so that is pretty specific, not a very general theorem, but still useful in many contexts. And I said, well, the boundary must have a certain structure. What exactly is that? Well, it must consist of finitely many closed and differentiable curves. So basically, if you look at something like that, right, say it's B is the disk here, and then the boundary of B is a curve, the circle, then of course that is just one differentiable curve. It's also fine if you have to split that in several pieces which are differentiable, right? So if you have to do that, you can do that. And then the second condition is B itself, so the area, the domain that you're interested in, is on the left of that curve at all times. So basically, if you walk along that curve in the direction of the curve, that is specified somehow, then if you look to your left, you will see into that set B. If you look to your right, you won't. Right? So that is what I mean by left of these curves with respect to direction of traversal. So some more examples. If you look at that rectangle here, for example, B is that set here, the rectangle itself. And then here's the boundary. And if you orient that boundary in this direction, right, then moving in that direction on your left, you will always have B. So that is the orientation the curve needs to have. In that example, so this boundary is obviously not a differentiable curve, right? Because you have those vertex points here that make things a little difficult. But you can split it into 4 curves. Here's one, that's the second curve, the third curve, and the fourth curve. So that's finitely many differentiable curves that taken together get you that boundary. Right? And a somewhat more exotic example is this here. Take that ring, for example. That has 2 boundary curves, one on the outside, one on the inside. Each of those is differentiable. And you can, of course, orient those curves such that your B is on the left, right? So for the outer curve, you will orient that in that way. For the inner curve, you'll have to orient that in just the other way. So that B is on your left. So that means the curves that compose the boundary don't have to be connected in a way. Right? They can be totally different curves as long as it's finitely many and they're all differentiable. Okay, so that would also be an example of a domain B where you could apply Green's theorem. And of course, the usefulness of Green's theorem lies in the fact that usually, or very often, one of those 2 integrals is easier than the other. So if you want to evaluate one of those and you find, well, the other would be a lot easier, then maybe it's an option to just compute the other one. One possible example is if the boundary, the B itself that you're interested in is a pretty complex beast and you don't find a nice description, but there is an easy boundary, then you might be able to replace that integral by this one here, evaluate that instead. Or also the other way around, if you want to evaluate this integral here, vector field over some curve, and the curve is pretty complex. For example, it's made up of a lot of different curves, and you would all need to add the integrals for those curves together, because you can't treat it as just one differentiable curves. For example, if you have that here, right, 4 different curves, you need 4 different integrals for that. It might be easier to just take a look at this integral instead, if you find an easy description for the B. In that case, that would be pretty easy, right? B is just a box. So that's easy to describe, whereas computing 4 different integrals for these 4 curves might be a lot harder. And of course, you'd have to come up with parameterizations for the curves. You don't have to do that if you can just compute this integral. So usually the application is one of the two integrals is way easier to get than the other one, and you can replace one by the other. All right, here's an example. You remember we've seen that already as part of the homework, or at least a similar problem here. You remember we talked about line integrals along the green curve here and along the blue curve here. And the setup here is somewhat similar in that we're again looking at these two curves. Now, the difference is the blue curve is oriented the other way. And that's because we're interested in this area between the two curves. And remember, for Green's theorem, we need that area to be on the left of our curves. So this is the orientation we want, right? The vector field is a different one than this here. Basically, apart from those two curves, there is pretty much no connection between that problem and this example here. It's just coincidence. So if we want to compute one of those two integrals here, either the integral along those curves or the integral over b, well, for the integral of the curves, what we have to do is we have to parameterize the curves. Basically, we did that here in the homework. Yeah, remember, this is one curve. In the homework, it was in a different direction. So, of course, that parameterization will be different, but similar. This here should be the same as far as I remember. Yeah, same curve. If you need to parameterize the curves, make sure you parameterize them in the way that b is on the left of the curves. That's the important part here. And then we can apply Green's theorem, which says if I want to compute this integral here, I can instead also just compute this integral. Right? And in this case, well, computing the integral over these curves would require me to evaluate two different integrals, one for each curve. Whereas this is just one integral, if I can come up with a nice description of b. And in that case, that description is not hard to get, right? Basically, that is part of a disk. So if you use polar coordinates to describe that, that should be straightforward. And of course, that is just what we can do here. So instead of computing that, I would rather compute this. And that means I just have to compute these derivatives here, right? Look at that vector field. Compute those derivatives, that's easy to do. The result is 2. So what you're doing is you're integrating 2 over b. Oops. And just as a side note, you will notice that you could take out the 2 here, right? So you could modify that, be 2 times that, so there's 1 in there, basically. And then this here, this integral would be the same as the volume of b, or the area in 2 dimensions, so we could also say area instead of volume. But again, that's just a side note, you don't have to know that. Question? Yeah. Exactly. So the domain is on the left of our curve, the boundary. That's only important when we apply Green's theorem, right? If you don't want to use Green's theorem, that is not relevant. If you compute the line integrals directly, it's not relevant which orientation they have. Just if you want to apply the theorem, you need to make sure the lines, the parameterization that you use has the right orientation. Right? So in this case, if we compute that, well, basically, this here should be pretty easy to do, right? Polar coordinates, simple transformation, simple integral. Whereas if you do that directly, you'll have to split the integral, right, using those two curves. And you have to use v of the curve and scalar product with the derivative of the curve. That's quite some effort. You'll end up, in this case, you'll end up fine. It's pretty easy in the end as well. But still, I think there's more to do than if you just use a nice definition of B. And of course, predictably, you end up with a result of pi, right? So that's basically why I remarked that here, the volume of the whole disk, radius 1, that would be pi. So what you get here is volume of half of the disk, pi over 2. All right. Another example, different vector field. This time we have a parallelotope. So the boundary now consists of 4 different curves that we need. Whereas the description of B, right, so if you describe that directly in Cartesian coordinates, B is a normal domain, as you can see. And that turns out to be pretty convenient. So instead of computing those 4 integrals for those 4 curves, I'd rather compute this. And as it turns out, right here you go, this is the difference of those derivatives here. And then you just use that definition of your normal domain, compute the integrals. It's a little work, but nothing that should be too hard. And there you get your result pretty easily compared to the curve integrals, I guess. Okay, so basically the idea of Green's theorem is to give you an option to replace one type of integral with a different one if that helps you computing the integral. Right, and one more thing about this is, of course, if you replace this integral by that, you do need to come up with a description of B, but you don't need to come up with a parametrization of the curves. And that might be pretty helpful if those curves don't look very nice. All right, questions so far? If that's not the case, then I would take a quick look at the homework problem, 13.2. Right, remember you voted, I think 50% of you voted this as challenging, so we should take at least a brief look. So the problem tells you to compute the integral of a certain vector field, v of x, given as, let's see, x1, x2, and x1 squared x2 to the third. Right, so that's your vector field. And you want to compute the integral of the vector field along a curve gamma. And gamma in this case is given as the boundary of the triangle with certain vertices. So the triangle is defined with the vertices 0, 0. Then we have 1, 0. And we have 1, 2, which is about here. Right, so this is our triangle. And it says in counterclockwise direction, so the movement along the curve is this way here. Right, so that's obviously a boundary of a compact set, this green set here. Non-trivial interior. Right, so we could just say this is our B. And All right, so here's your triangle. You remember we discussed integration over triangles in a number of examples, so that should not be challenging. Of course, what we need is a description of that set B. And in this case, well, I guess one easy option would be to say, well, the x1 coordinate is between 0 and 1. And then the x2 coordinate is between 0 and whatever this line is. So all x in R2, where x1 is between 0 and 1. And x2 is between 0 and, well, let's see what a line is. We want that here. Obviously, that goes through the origin. So that can be described as x2 is slope of the line times x1 plus 0. The y-intercept will be 0. And what we have here is, well, if you move 1 unit to the right, we move 2 units up. That means the slope is 2. Right, so that would be the equation describing that blue line here. And that means the inequality for x2 is to be below that line. So what we want here is x2 is less or equal to 2x1. Right, so we have an easy description of B. And that means we can use Green's theorem now. This orange thing here, that's our gamma curve. So the integral of v of x ds along that gamma curve is, by Green's theorem, the same as the integral over b. And remember, we need dv2 dx1 minus dv1 dx2. That's the formula here. dx1 x2. So let's briefly compute that. V is this integral here, right? So dv2, this is v2. If you differentiate that with respect to x1, well, we get 2x1 x2 to the third. And then dv1 dx2, so this here is v1. Differentiating that with respect to x2 yields just x1. So it's minus x1. Okay, and we need to integrate that here. And now we use the definition of b that we came up with. This here depends on x1, so this needs to be the inner integral, and this here, x1, depends on just constant, so this needs to be the outer integral. That means we're integrating with respect to x1 from 0 to 1, and then x2 from 0 to 2x1. And we're integrating this expression here, which is again 2x1 x2 to the third minus x1 dx2 dx1. All right, so let's evaluate the inner integral. Integrating this here with respect to x2. Here we have x2 to the third, so we get x2 to the fourth divided by 4. So that's 2 over 4 x1 x2 to the fourth minus x1 x2 from 0 to 2x1 dx1. So evaluating that, 2 over 4 is 1 over 2. So we have 1 over 2. And then we substitute 2x1 for x2. So we get x1 times 2x1 to the power of 4 minus x1 times 2x1. And then for the lower bound, well, if we substitute 0 for x2, we just get 2 zeros here, right? So that's 0 minus 0 dx1. So simplify that maybe just a little. All right, so here we have, let's see, 1 over 2 x1. So that's 2 to the 3, that's 8 times x1 to the power of 5 minus 2x1 to the power of 2 dx1. Now we're ready to integrate that. X1 to the power of 5, if we integrate that, we get x1 to the power of 6 over 6, so that's 8 over 6, x1 to the power of 6, minus, and here we have x1 squared, so we get x1 to the power of 3 over 3. So that's 2/3, x1 to the third, from 0 to 1. So what we get is 8 over 6 is 4 over 3 times 1 minus 2 over 3 times 1 minus, well, and the other boundaries again, 0 minus 0. So that's 4/3 minus 2/3, which is 2/3. Right, so just one integral, and a pretty simple one. It's just polynomials after all, right? Just have to pay attention and keep up your concentration to not make any mistakes. But conceptually, that should be easy. Probably easier than finding parameterizations for those 3 lines here and then integrating the vector field along those lines. You could also do that, but I think that is the far shorter way. Did anyone try evaluating those integrals directly? Yeah? Sorry? It also worked out. How was it longer than what I just did? Okay, it was good. All right, any questions about that? Let's take a quick look at tweetback. So one question is, for Green's theorem, should the vector field be a gradient field? And the answer is, it doesn't have to be. As long as it's differentiable, so let me get back to Green's theorem here. What you need is basically, you need a set D to be open. B needs to be defined on some open set that is basically larger than the B that you're interested in, actually. And it needs to be continuously differentiable. It doesn't have to be a gradient field, right? It will work for any vector field. And of course, you will notice that if it is a gradient field, well, what happens if it is a gradient field? Then you know the integrability condition holds, right? That means dv2 dx1 is the same as dv1 dx2. That's exactly the integrability condition. If you have a gradient field, that part here will be 0. And that should not be much of a surprise, because what we have here is always, we have a closed curve, right? So this boundary of B is always a closed curve. So you're integrating a vector field over a closed curve. If that vector field happens to be a gradient field, the integral of a gradient field along a closed curve is always 0, right? So that's exactly what happens here. You get a 0. So for a gradient field, that's trivial when you don't need Greek theorem, but it will do the right thing, of course. The more interesting applications are for non-gradient fields. And again, Green's theorem is something that works in 2 dimensions, so in R2. There are generalizations of that theorem to higher dimensions, but we will not talk about those. You might encounter these in some applications possibly. So similar theorems in other contexts, like these different settings or different dimensions, that are also pretty famous are Stokes' theorem and Gauss' theorem. You might encounter those similar ideas, but generalized to a little different settings. Yeah, but I guess for this course, it's enough to see the idea at least once, and Green's theorem is the easiest one of those. All right, any more questions about that? Otherwise, I'll give you an exam problem that you can work on. And meanwhile, I'll browse through the questions on TweetBack. So here's something that you can try from a 2020 exam, a line integral over a vector field. So see if you can figure out the solution. Give you a couple minutes to solve that. And as usual, I forgot to mention there is a TweetBack quiz asking for your answer for that problem here. All right, quick progress check. Who's done? That is not a lot. Who's still working? So I guess we'll give it a couple more minutes then. So let's say 1 more minute. All right, time's up. So here is the results of your vote. A couple of votes for wrong results. The last one, which most of you recognize, is of course the right answer, 9 pi over 8. So let's take a quick look at how to do that. As you can see, basically there's 2 options. You could attack that one. We have these curves here. If you want to do it manually and parameterize those curves, that's this one, and this one. So you need to come up with parameterizations for these 3, and then you can, of course, compute the line integrals more or less by hand using the definition. As you probably guessed, that is not the intention of this problem, right? That seems awfully complicated. So in a case like that, especially as the parameterizations are not given, you would first have to devise those. I'd say there's a good probability that one of 2 cases will help you solve that problem. Either it will turn out that this vector field is conservative, And then you know integrating a conservative field along a closed curve, that's 0. So that would be a solution if that happens to be the case. Or, as in this case, this is an application of Green's theorem. So of course, even if the problem statement doesn't say use Green's theorem, you are free to do so if it helps you. And in that case, that is exactly what I would do. Use Green's theorem means I don't have to come up with these parameterizations. Instead, I have to come up with a nice way of describing this B here. But basically, that's part of a disk, so that shouldn't be hard. Okay? So that's what we're going to do. As you can see, if you follow this curve here, B is always located on the left of the curve, right? So that is already fulfilled. Furthermore, that B is a compact set. This vector field V here, that is easily continuously differentiable. And it consists of, this curve consists of 3 pieces, which are also continuously differentiable. Yeah? So that should all be fulfilled. So we can take a look at the theorem, which says, well, this integral that we want is exactly the same as the integral over B of dv2 dx1 minus dv1 dx2. And then if the vector field happens to be conservative, once we compute that, this expression will become 0, so we will be done anyway, right? So we don't have to take care of that separately. The theorem will do that for us. So let's just compute that. And if we do that, well, this V2 is this one here. If we differentiate the with respect to x1, we get 3x1 squared, and then minus, this is V1, and differentiating that with respect to x2, well, there's no x2 here. So this is minus 3x2 squared. And basically this is almost the only part where you really need to pay attention. That's a minus from that formula and a minus here from the differentiation. Right? Don't forget that. So simplify this. Well, not much simplification to do. Basically, you can take out 3 if you want to, and then you get x1 squared plus x2 squared dx. So it's not 0, right? That means the vector field is not conservative, and we have to go through all the motions of Green's theorem. All right. So we need to come up with a nice description of B. Well, this B here, as I said, this is part of a disk. So the radius obviously is 1, right? This goes through 1 here, or minus 1 rather. The radius of that thing is 1. We exclude this part, or we could say we include everything between this angle, and this angle is pi over 4. And this angle, right, which is 2 pi minus pi over 4, or 7 pi over 4. So we can say B in polar coordinates. Can describe that as everything where the radius is between 0 and 1, and the angle is between pi over 4 and 7 pi over 4. And then we just need to evaluate the integral, right? So continuing this one here, we want to transform that into polar coordinates. And if we do this, well, x1 squared plus x2 squared, yeah, this is the norm of x squared. The norm of x is equal to the radius, so this is r squared in polar coordinates. Okay, so what we get in polar coordinates is where we integrate, doesn't really matter which direction we use, let's do the r as the inner integral. So phi as the outer integral. The other order would work is fine, this one, so r from 0 to 1. And then we integrate over, well, the function is just r squared. And then remember, we have to multiply by this determinant of the Jacobian, or the absolute value of the determinant of Jacobian of the transformation, which is just r for polar coordinates, right? So this is r squared times r. Maybe let me mention that. That is the determinant of jt and the absolute value of that. This one here, that's the change of variables formula for integration. If we change, so see, we integrate using Cartesian coordinates. So if we change the integral to polar coordinates, we have to apply this change of variables formula. And that requires us basically to add this correction factor here for the transformation. And for polar coordinates, that is r, or the absolute value of r, but well, r is between 0 and 1, so the same thing. All right, so we need to integrate that, dr d phi. Well, and that means, let's copy the outer integral, 7 pi over 4. So we have r to the third to integrate. That means this is r to the fourth over 4. And I just noticed I forgot to copy this 3 here. So let me add that. There should be a 3 and there should be a 3. It's this one. All right, r from 0 to 1, d phi. So evaluating that is thankfully very easy. R to the 4 over 4 for r equals 1, that's just a quarter, minus 0 for the lower bound. And again, I forgot the 3. Right, so integrating that with respect to phi, well, there's no phi in there, so that the integral is just phi times the constant. So if we also take out the 1 over 4, we have 3 over 4 times phi boundaries from pi over 4 to 7 pi over 4. And then all we need to do is evaluate that. Well, that is 7 pi over 4 minus pi over 4, which is 6 pi over 4. And that should be, let's see, that's 18 over 16 or 9 over 8 pi. So that is the final solution. And again, you could do that using the formula for line integrals if you want to. You'd have to come up with parameterizations and then compute 3 different integrals. That is an option, but it probably takes a lot longer. Any questions about this problem? Yes. So I'm not sure if I get the question correctly, but I'll try to answer it, and you tell me whether I got it. So part of the question was about the order of integration, right? So I choose to have the integral over r as the inner integral and then phi as the outer integral. The boundaries in this case are constants, so there's no dependence on each other, and that means the order of integration doesn't matter. You could also use it the other way around. That's fine. She'll give you the same result. The reason why I did that is basically because I have a 0 as lower bound here, so I was expecting this to be rather simple, and this might have been more complicated to evaluate, but that's largely a matter of taste, right? You could interchange the order and it would still be fine. And then you said something about this part here, right? Gamma, so the arrows indicate the direction of gamma of t as t increases. What I meant to say by that is that the orientation of the curve is in the direction of these arrows, right? As t increases, well, if I go from 0 to 2 pi in this interval. So the only part where this is important is you'll have to notice that the b, this area here, is in fact on the left of the curve. And for that, the direction of the curve is important. And of course, as t increases, well, that is the usual way these things will be evaluated, right? Doesn't make a lot of sense to have t decrease. Did that answer the question? Good. Yes. So in the exam, if you want to use Green's theorem, of course, you should be sure that the set is compact, and it doesn't hurt to mention that. The very least thing you should do is mention that you're using Green's theorem, right? Otherwise, I had a couple of cases where people, I think, attempted to do just that, but didn't write that, neither that, and didn't mention Green's theorem. They just wrote down some integral here, and they made an error somewhere. So that was wrong, and it was not obvious at all what they were trying to do. So they were not getting any points, not even for effort. So at least mention what you're trying to do, write down the formula first, and then apply it. That might at least give you a point for trying to do the right thing. And then maybe consecutive errors afterwards, but if you start out with something completely unrelated, and the corrector can't tell what you were trying to do, then that's probably just the end of it. Any other questions? Yes? So the question is, why can we use polar coordinates? And what about those straight lines? Well, my point is, I'm using polar coordinates because they turn out to be convenient. I could do this in Cartesian, but it's not that convenient. Give it a try if you want to see. What I have to do is I have to describe this normal domain here, right? This blue B. I do not have to describe these lines. There will be something different. This is the boundary, right, of my domain, but I don't have to explicitly describe the boundary. So all I have to do is I have to characterize the points inside of the blue set. And then it's rather easy to come up with a description in polar coordinates, because I can say basically this is the disk, right? Just this little part here that is missing. And how do I characterize this missing part? Well, radius is clear, it's just a disk of radius 1, even for the missing part, so that's fine. And the missing part is just the one with angles between 0 and pi over 4, and with angles between 7 pi over 4 and 2 pi. That's what's missing. So in other words, what I have is just the opposite. Everything between pi over 4 and 7 pi over 4. Right? And so basically these parts of the boundary are characterized by the angle. Did that clarify things? Great. Yes. So if the boundary would be oriented that way, right? You change the orientation. You could still use Green's theorem by just applying a little trick and saying, well, this red gamma, the other way, the integral of that is the same thing as the one for the, I'll just make it blue, the blue gamma, but changing the direction, that changes the sign, basically, right? So if you change the direction of the whole curve, that would just change the sign of the integral, and then I do this transformation, and I'm back to the right curve. Yeah, then I could use Green's theorem again. Any other questions? That doesn't seem to be the case. So let's take a look at a couple more problems. Here's one from 2016. That's in German, but I think it's clear what it says. It asks you to use Green's theorem to evaluate this curve integral here. This is the function f, or the vector field f. And k, this k here is the boundary of a triangle with these points. And it says here that's positively oriented. So positively means counterclockwise. It's mathematical positive. Right? So this is your triangle. The boundary of that in counterclockwise direction, that is k. Compute this integral. Go ahead. And by the way, that is again, what do you mean with 10 points? And again, there's a tweetback quiz asking for your answer. Usual question, who's done? Who wants some more time? So let's give it one more minute. All right, so here's your answer. Most of you said 32 is the right answer, and that should be correct. So let's quickly take a look at how to do that. In this case, it explicitly asks you to use Green's theorem. And by the way, whenever you have a description of a domain, it's always a good idea to first get an idea of what that thing looks like. So if possible, I would always try for a quick sketch, right? That's what I did here. So this curve here is our K, and indeed positive orientation. So to the left of that K, we have this triangle here. Maybe let's call that green thing T. So that's the triangle itself. And using Green's theorem means, well, if you want to integrate V over that curve K, that is, oh, let's call it F, not V, sorry. I want to integrate F over that curve K. That is the same thing as integrating over the triangle T. The expression df2 dx1 minus df1 dx2 dx. And that's just what we're going to do here. We need to come up with a description of T, of course, right? So to get that, well, notice it's a triangle, so in this case, it's probably most convenient to have x1 between 0 and 4, right? So this is the constant part here. So it's all x in R2, where 0 is less or equal to x1 is less or equal to 4. And then x2 is between 0 and this curve here. So 0 is less or equal to x2 is less or equal to that curve here, this line here. Again, that goes through the origin, so we can describe that as x2 is slope times x1. And the slope, well, we move 4 units to the right and 2 units up. So that means if we just move 1 unit to the right, we would move a quarter of 2, so 1/2 up. That means the right expression is x2 is 1/2 x1. So this is the right boundary here. Okay, so if you want to integrate that, that means x1 is going to be the outer integral from 0 to 4, and x2 is going to be the inner integral from 0 to 1/2 x1. Right, and this time the order does matter because this bound still depends on x1. Now to compute this part here, so f2 is 2x1 squared x2, differentiating that with respect to x1, we would get, let's see, 4x1 x2, and then minus f1 x2. So this is f1, differentiating that with respect to x2. Well, there is no x2 in there, so that's just going to be 0. dx2 dx1. And now all that's left is computing this integral. So for the inner integral, the x2 integral, well, x2 integrated is x2 squared over 2. 4 over 2 is 2, so we get 2 x1 x2 squared. x2 from 0 to x1 over 2. So this is upper bound. That's 2x1 times x1 over 2 squared minus, and well, the lower bound is 0, dx1. So what we get is, let's see, x1 from 0 to 4. That's 2x1 times x1 squared, so that's x1 to the third. And we have 2 and then 1/2 times 1/2. So that is 2 over 4 or 1 over 2. x1 to the power of 3. And now let's integrate that. We get x1 over 4 to the power of 4 over 4 from 0 to 4. Or we'll take out the 1 over 4, then we have 1 over 8 times 4 to the power of 4 minus 0. So what we get is, let's see, 4 to the power of 4, and 1 over 8 is 4 times 2, so we get 3, you get 2 times 4 to the power of 2, which is 2 times 16, which is 32. Right, so 32 is indeed correct. Any questions about this problem here? Maybe just one little remark here. So as far as I'm concerned, I'd say 10 points is a little much for that. I would probably have given that a few less points. It's rather easy, I guess. Easier than the first problem you saw, in my opinion. All right, so if there's no more question, I have one last problem here. Again, take a quick look at that. No tweetback quiz this time, because there's no number you could come up with. 2 of you is done already? Who's still working? So let's take 1 more minute or so. All right, so let's try to solve this one. First, we need to express B in polar coordinates. So if you look at B, I mean, you have a sketch down here. You see x2 is basically above those 2 lines. That's greater or equal to the absolute value of x1. So we're somewhere here in that cone. And then x1 squared plus x2 squared is less or equal to 8. So you know this is the norm squared. And that means, and this is one that many people didn't recognize, that means the norm is not less or equal to 8, but instead square root of 8. Right? You could also see that in the sketch here. Well, this is a little below 2. 2 is 3, sorry, a little below 3. 3 is the square root of 9, so that should correspond to the square root of 8 nicely. So if you want to express this in polar coordinates, again, that's part of the whole disk. And that means you can express this as dr phi again, where the radius is between 0 and the square root of 8. And again, people forgot about that square root. Don't make that mistake. And the angle, obviously, well, this is pi over 4, and this is 3 pi over 4. So the angle is simply between pi over 4 and 3 pi over 4. Right? So that's easy enough. And then in part B, I'm asking you to apply Green's theorem for this integral here. So integrate the function f, this one here, along the border of B, where this border is traversed in counterclockwise direction. So I'm traversing this border in this direction here. Right, this is the border of B in counterclockwise direction. So obviously B itself is to the left of that border, right? And that means I can directly apply Green's theorem. Say, well, this integral here on f of x, it should be ds actually. Used a different notation back then. That is equal to the integral of b over, again, using Green's theorem here, df2 dx1 minus df1 dx2 dx. And this is, well, if we look at f, this is f2. Differentiate that with respect to x1, and we get x1 squared plus x2 squared. So x1 squared plus x2 squared minus and df1 dx2. This is f1. That doesn't have an x2, so the derivative is 0, minus 0. And then we just need to use the definition of b that we came up with in the first sub-problem here. Everything is constant bound, so the order of integration doesn't make a difference. We can use anything we want here. So for example, r from 0 to square root of 8, and phi from pi over 4 to 3 pi over 4. And of course we have to transform this into, oops, there's a square missing, sorry. We have to transform this into polar coordinates. So we already had this before, x1 squared plus x2 squared. This turns out to be r squared. Right, so we have r squared. And then again, don't forget this correction factor, right? The determinant of the Jacobian absolute value. This is this r here, d phi dr. So if we simplify this just a little more, what we get is the integral over r to the third. Right? And quite a few people forgot about this factor here. Don't make that mistake when you do transformation to polar coordinates. Yes? For what, sorry? For the first, maybe I didn't, could you, so you're referring to some different exercise, right? Oh, this one here? So what's the question? The correct notation for what? Oh, you mean something like all r phi with and then the same thing here? Oh, how would you write that down? Oh, if you wouldn't write that as a set, but instead just write down those, yeah, you would also have gotten points for that. So I like this a little more because it does capture the dependence, if there is one, a little better. And also by this transformation, basically that's a reminder for myself to not forget about this correction factor when I transform the integral. But if it's sufficiently clear what you mean by B and what that should describe, then that's also fine. Yeah. All right. And just one more remark. It says here explicitly, transform the resulting integral into polar coordinates, so you should absolutely do that, including the integration limits, and simplify the integral. You do not need to solve the resulting integral. Right? So while, of course, you should all be able to solve an integral like that, it's completely fine to do that, and it's a complete waste of time in an exam. It's nice practice if you want to try this at home, but in the exam, please read the problem statement and then do exactly what the problem statement asks for. Don't waste your time on things you don't have to do. Yes? So you mean, can you change this order? Yes, you can. There is, so all the bounds are constant, so there's no dependence here, and you can choose any order you want. That's fine. The result will be the same. Any other questions? Wonderful. So if there's anything you want me to discuss next week, don't forget about that tweet back for week 14. I'll take a look at that and try to prepare at least the Monday lesson tomorrow. So if there's anything urgent, preferably post that today. And of course, you're also free to vote on the remarks and the questions that your colleagues have already posted, so that I get an idea what we should discuss first. Right? Otherwise, if there's any more questions, you're welcome to stay for exercise classes, which will also take place once again next week. So you'll have an opportunity to get answers to any questions you might have then. And otherwise, I'll see you on Monday.